Guys, today we're going to look at a process called completing the square so that we have an option to change functions in standard form into vertex form. Something that we are not looking at in your notes is actually how to get the vertex directly from standard form. There's a little formula that we can use, but rather than having you focus on trying to memorize the formula, what we're going to look at instead is a process called completing the square. So if you could take a look at page 47 with me, we're going to talk about this process called completing the square. So we use completing the square to be able to change a function from standard form into vertex form. And so as we look at this with our first function, we're actually going to look at this with sort of a geometric idea, completing the square, right? Square is a figure. We have some familiarity with that idea of a square. So we're going to take a look at why it's called completing the square, this process that we're going to look at. So here's our function that we're going to work with. So this is standard form right now. Remember, from standard form, I can see the y-intercept, but in order to get x-intercepts, I would need factored form. In order to see my vertex, I would need vertex form. So we're going to look at how to change this into vertex form with this process called completing the square. So each of these terms we could represent geometrically. We could represent with, say, an algebra tile. This x squared piece would be a square that's x by x, okay? If we thought about its area, that would be x times x, which is x squared. This 6x piece we could think about as being a rectangle that is 6 by x. If we thought about its area, 6 times x would give us 6x for its area. Now, the problem is that if I put these two pieces together, I have a rectangle and not a square. And what we want for vertex form is something that's in parentheses and squared. Remember, for vertex form, we need something squared, right? Our goal is to have our function look like this. So we need something squared, okay? This is a rectangle, not a square if I put those pieces together. So what we're going to do is take this piece that's 6 by x, and we're going to cut it in half. Okay, we're going to cut it in half, sort of vertically here. And so then I get two little rectangles that are each 3 by x. So the area here would be 3x on each of these. And then what we're going to do, since we cut this large box in half, is take and align one piece along the side and align the other piece along the bottom. So that's what we see here. There's our x squared box, and then our 6x box that's been cut into 3x and 3x. Okay. And so here we have a better shot at creating a square because now this side is the same length as this side, right? Instead of having a box that's x plus 6 and x, we've got x plus 3 and x plus 3. And the only problem is that we've got this sort of empty space here. So what we need to figure out is what area do I need to complete the square? That's why it's called completing the square. So we know that this little space down here, this sort of shaded gray area, would have dimensions of 3 by 3. So the area of that space would be 3 times 3, which is 9. So what we've done here is say, keep the x squared box, split 6x into 3x and 3x. Okay? And we have some familiarity with that from AC method, where we split that middle term into two pieces. This time we're just splitting them into equal pieces. And then what we need to add on would be the area that I'm missing here, which would be 9. Now, algebraically, to keep our expression balanced, remember that we also had this -1 here at the end. And if I add 9 to something, that changes it. So if I want to make sure that I've maintained balance in my expression, I haven't changed it, I've just sort of rewritten it, what we need to do then is if we add 9, we also have to subtract 9. Okay? So here's geometrically what's happening, and here's how we can represent this algebraically. Again, remember this was our 6x piece that we just split into 2. We're saying we need 9 to actually make a square here, okay? And since we added 9, we also have to subtract 9. Now, what this is going to look like if we kind of fall back on our factoring, just recopying that problem, is that now we have something in 4 terms, that we know how to factor. So for terms, I'm going to use grouping. My GCF for the first group would be x. I'm left with x plus 3. My GCF for the second piece would be positive 3. I'm left with x plus 3 when I factor that out. My stuff in parentheses is the same, so I have x plus 3 that I'm going to pull out. And then left over, I have another x plus 3. Here at the end, I'm just going to combine these like terms. So -1 and -9 would be -10. And then remember that if I have the same factor twice, I can actually just write that as a square, x plus 3 squared minus 10. Well, now I have my function in vertex form. Okay? I can see that my vertex would be -3, comma, -10. So what we're going to do is practice this algebraic process. Something else I want you to notice, though, is that our side length for our square would be x plus 3. And here, same thing. I've got x plus 3. Notice that that's what we end up as our factor here, x plus 3. Okay? So I shouldn't be shocked that I ended up with x plus 3 squared here. So we're going to do a couple more practice problems of completing the square. So on the next page, we're going to take a look at those examples on the top of page 48. Okay, so we're going to change these functions to vertex form using that completing the square process. So for our first example, I've got x squared plus 8x plus 2. I'm going to start by splitting this first term in half. So that would give me x squared plus 4x plus 4x plus something, whatever completes my square here. And then at the end, I'm going to put this plus 2. And whatever I added here, I'm going to have to subtract off at the end. Now, how do I figure out what goes in this space? What's going to complete my square? Well, if we go back to our geometric figure here, I want you to remember that we got the area of this thing by taking our split in half numbers and multiplying them together. So since we split a number in half, we split that 6 in half, we got 3 and 3. So essentially we took 6, split it in half, and squared it. So this is going to be 4 squared. 4 is what we got from splitting 8x in half. And now if we thought about our picture, this we know is x, this is 4. This guy's also got a width of 4, so this little box here would be 4 by 4. So with area would be 16, okay, or 4 squared. So I'm going to fill 16 in here. Since I added 16 to my problem, to keep it the same, I'm going to have to subtract 16 off at the end. So adding 16 and subtracting 16 from the same expression doesn't change it, right? And now I can use either my factoring, like I did on that first problem, or if you are a picture person and you like to visual, remember that the sides of our square are going to be x plus 4. I'm going to walk through that factoring again, just for some extra practice with a grouping strategy. So if I pull up my GCF here, that would be x. I'm left with x plus 4 when I factor that out. My GCF for that second group would be positive 4, leaving me with x plus 4. My stuff in parentheses is the same, so I can pull that out now as my GCF x plus 4. Left over, I've got x plus 4, which I should expect, remember, because I want, for vertex form, the same factor twice. And then here at the end, when we combine our like terms, 2 minus 16 would be negative 14. So just to finish tidying this up so it looks like vertex form, I would have x plus 4 squared minus 14. Okay, there's my vertex form. My vertex here would be negative 4, negative 14. We'll take a look at one more example together for today. Our last example for right now, we've got x squared plus 10x minus 3. So I'm going to do the same thing I did before. I'm going to take this middle term and split it in half. So I would have x squared plus 5x plus 5x. And then I'm going to have to add something in to complete that square. And then I'm going to push this minus 3 to the back of the problem. And then I know whatever I add here, I would also have to subtract at the end. So this number that I fill in the blank we talked about is always going to be this b cut in half and squared. So this is going to be 5 squared, which is 25. And since, again, I added 25, to maintain my balance here, I have to subtract 25. And then you could factor by grouping it again, like we did for the last two problems. Or you may have started to notice this sort of pattern, this little bit of a shortcut here that we can take, which is that my factors are going to be x plus 5 times x plus 5, or just x plus 5 squared. And then combine our like terms at the end, we would get minus 28. So there would be our vertex form. Now, if jumping straight to that factored form is a little bit too much for you, go back and factor using our grouping strategy. You're going to come up with the same factors. You're going to combine like terms at the end to get that same negative 28 that I got here. But if you kind of recognize the patterns that we've seen a little bit, you can jump to here. This is going to be our middle term cut in half. And then at the end, we're going to take whatever that middle term cut in half is, square it, and subtract it. So here's our vertex form, and our vertex would be negative 5, comma, negative 28. So that's completing the square. What I do want you guys to notice is that every problem we've looked at so far has had an A value, a lead coefficient of 1. Okay, we've had a lead coefficient of 1 for all of our problems we've looked at so far. Next time, we'll look at lead coefficients that are not 1. There's a little bit of an extra step that we have for that process, but for right now, we're just going to focus on when the lead coefficient is 1. This is our completing the square process. Okay?